models of motion. So we're going to start off with this man, Usain Bolt, who as of 2026 is still the world's officially fastest man. I think this is the 2012 Olympics. I think he's defeating everybody, running an amazing time for for a sort of like a cold London rather than a sort of hot country. And he ran only about 10th per second quicker in Berlin. You can see the different colour of track there, which still stands at the amazing 9.58 seconds. So I use this as a little paradigm example when I'm teaching mechanics to my students at Winchester, because it's really nice, because it really talks about what kinematics is, which is the study of motion, from kinema, from the Greek. And so what does that mean from a kind of computational perspective? So a very nice, I think it was an Australian actually, who sort of diligently videoed Usain Bolt's world record 100-meter races in 2008 and 2009. I think 2008 was in Beijing. Oh yeah, there we go. And every 10 meters, you have these sort of lines. You can't quite see one in the picture here, but take it from me, I used to do quite a lot of athletics. And every 10 meters, you have a nice painted line across the track. So this is good from a science perspective, that you can work out what time has elapsed during that race. Now, obviously, we'd want to do this, every meter or every millisecond or something like this. But so it's not a very well sampled data set. However, this gives you some idea of what's going on. So if you plot displacement versus time, which is quite nice because it's straight down the track in a straight line, we're not having to worry about two dimensions and curves and that kind of thing, we get something that looks quite straight, and you can just about resolve the two races. Obviously, in 2008, he took a little bit more time. And there's a bit of curve at the start as well, but it may look like the sort of velocity, the gradient of this graph is quite similar. Now, what you can do is you might say, well, okay, well, how fast does he actually run? What does that mean? So I'm sure we all know that the gradient of a displacement time graph is what we call the velocity, and that could be instantaneous, all right, at a given time. So what we can do computationally is fit curves to this line. And I've done this by fitting something called a cubic spline. So this is essentially a cubic to every 4 data points. And you can sort of work out that recipe using a bit of calculus. A lot of computer programs have this built in. So that's quite a nice way of fitting a curve to a set of data. But you could keep this a bit more simple if you like. But essentially, we're using a computer to numerically differentiate this. And the simplest way of doing it is taking 2 data points and doing the kind of like rise over the run between 2 points here, and then doing y equals mx plus c. So, if you're doing this for the first time, that's something you could code up in a little graph. Anyway, so we can numerically differentiate a set of data if we don't know the underlying curve. And so this is what I've done. It's about just 3.5 seconds, something like that. So he's going amazingly fast, 11.2 meters per second. All right. And what we can do is we can do that all the way along this line. And that means we get something rather more interesting than a kind of vaguely straight line. We start to see some structure. And because it's kind of in the middle, the velocity time graph is really where you want to start with kinematics and models of motion. We differentiate it, we get the acceleration, which relates to mass times acceleration as vector sum of force in Newton 2. If we find the area under it, the reverse process of differentiation, we get the distance traveled and hence the displacement if we're talking in a straight line. So the velocity time graph is really where you want to start. We're going to meet this again for some bouncy balls later on. So this is quite nice. And I usually like to start with this example because it's not straight. It's not a straight line graph. It's not even a kind of trapezium, which is the sort of thing you find in exam papers for good reason, because you can easily work out gradients and areas. In reality, we're going to have some curves. And in fact, although we've got quite a badly sampled data set, if you just look again, we've got, about 10 data points. I think there's enough evidence to sort of say that he kind of speeds up and slows down a bit in 2009. So you might conclude that even the fastest 100-meter ever run by a human that we know of, actually he might have even run that even quicker. So possibly he sort of like stood up a little bit too quick, some sort of aerodynamic, some braking, a sort of drag he might have experienced. It's all kind of very small things, but we're talking about the world record here. So looking at the velocity time graph gives you all the information for analysing kinematics. So we're starting with the person, but of course, if you were into Formula One, you might be looking at the performance of your car. If you're designing rockets, it might be, with their the SpaceX program, they'll be looking at telemetry for this from every launch. So I think this stuff is fairly applicable. So we've met numerical differentiation. Let's do it again. And if I take cubic splines of this curve and I work out the gradient of my cubic, which will give me a quadratic, I can work out my acceleration versus time graph. And again, you could do that more simply by literally just doing the rise over the run between pairs of data points. And what you'll get is quite noisy data here because we've only got 10 data points. So the ups and downs after about 3 seconds, I think we can sort of, not really give too much credence to, but there are some features we can. So it seems like he has a maximum acceleration of about 5 meters per second squared, about half a g. And then in 2008, he slowed down. And if you've ever watched the video of this, infamously, he crosses the line, kind of like strolling around with his arms in the air, having broken the world record rather spectacularly. So that's quite a thing to do. So there we go. That might be a really nice start of kinematics. So what have we got? We've got velocity, we've got displacement, and we've got acceleration. And we've got kind of gradients between those. So if you want to plot this, and I've used MATLAB to plot these graphs, Python, all those things can be used as well. You'll notice they've got the same scale in time, so you can pair them together. And you can go for, if you differentiate, so you go from the displacement to the velocity to the acceleration. You integrate, you've got the acceleration to the velocity to the displacement. Right? And that's sort of getting your head around all of those really is a very solid starting point for kinematics. So that's kind of where we're going to begin. I've got quite a few sort of case studies of apps and code of things we might produce in terms of motion here. So before we look at the second example, which is all about Jeff Bezos's Blue Origin launch, do we have any questions from the chat that I can deal with straight away?
No, not yet.
Not yet. Okay, fantastic. Right, so there we are. Here's one of the world's richest men who famously, or perhaps infamously, sort of went into space, I think it's a few years ago, 2021. So Blue Origin, a bit more secretive, perhaps, you might argue, than Mr. Musk's rival company. One thing that was quite nice about this launch is that the telemetry, so in other words, the altitude, velocity, and acceleration, well, certainly the altitude was displayed on a video live. And then that was released on YouTube. So I sort of spent some time going through this and constructed a little spreadsheet. And so it's quite an interesting one because he goes up just over 100 kilometers, and this is a wonderful, almost parabolic trajectory with time. And if you differentiate that using exactly the same ideas that we talked about, in fact, it's even simpler in this spreadsheet. I'm just literally doing the difference in the altitude. Actually, no, it's you can see it here. So there we are. I've got the difference in velocity divided by the difference in time, and that gives you my acceleration. And the velocity, I think I might have actually got from the in miles per hour. So I think I got that from the recordings rather than numerically differentiating this. So we get a slight bit of noisy graph for acceleration, but you can kind of see the velocity increases in a sort of almost sort of quadratic-y kind of way, and then we have this sort of linear decay of velocity. So essentially, it's under free fall. And that's kind of the idea, is that it's sort of set to kind of fall. No, it quite probably won't be exactly. Well, actually, it is kind of about 10 meters per second squared. We're not that far away. We're only 100 kilometers from the surface of the Earth. So as a fraction of the radius of the Earth, that's pretty small. So a G will be a little bit smaller, but probably on this scale, not easy to see. So essentially, he's in free fall for about 300 seconds, something like, maybe a bit less, 270 seconds. Where they can all float around and pretend to be spacemen. And then we re-enter the atmosphere, and there's a bit of acceleration, and then it goes back to Earth. So kind of like a bit of a very expensive sort of fairground ride. But maybe this will be the future in getting cheap transportation to the stars. Who knows? But anyway, so there's a lot of data out there, and find something you're interested in. Get some displacement or velocity versus time data and differentiate it and integrate it and see what you can find out. Even better, if you can get yourself a cheap data logger, a lot of phones will act that way with accelerometers. You can record your kinematic data yourself and have a play with it. There's some really good stuff actually you can get for free. So if you've never done that, maybe you could just jog around the track or go on your bicycle or perhaps in your parents' car and record some data and see what happens. And obviously, if your parents are breaking the speed limit, perhaps you may not want to release that on the internet. Okay, right. So number 3. Oh, there we go. There we go. That was the team of astronauts. So there we go. Altitude versus time, velocity versus time, and acceleration versus time. And there we go. Right. So in summary, and I'll read this. Kinematics provides a really good reason to wish to know velocity or acceleration from displacement measurements, i.e. the gradient of the underlying curve. We may not know the functional form of the curve, however, we may have to estimate it from the data. All right. So in the bolts example, we fitted a cubic spline, and we can then differentiate the cubic to yield a quadratic and integrate the cubic to get a quartic. Or in the Bezos example, we just did a straight line between velocity measurements, and that's how we got acceleration. So, you can make things a bit more sophisticated, but you might not actually get much more data. If you had a really high data rate, just doing rise over run between points is going to be fine. Okay, so let's have a go at this. So before I talk about the code, let's have a little look about what this experiment's all about. This is basically about dropping a basketball, a slightly flaccid one, and recording what happens. So I have a little picture of this. I hope it's now gone. Let's go and minimize my screen, and you should see another 2 of these. There we go. So hopefully you can see me in my lab in Winchester in P5. So I have the oldest ever basketball. By the way, can I just check, am I still broadcasting okay, guys?
Yeah, all good.
So what we've got here is the amazing lab tech, Mr. Chesters, has now painted this rather old-looking, tatty-looking, but enormously tall retort stand. So this is for those, if they want to do my bit for Winchester College to promote the amazing school. It looks a bit less tatty now in our laboratory. So what we've got is this blue thing, and that produces ultrasound. So I think it's above about 20,000 hertz. So we can't really hear it. And what that will do, these little pulses are produced, quite a high data rate, and will bounce off things like this very ancient basketball. And so what you do is you hold it in the beam and you press go. So there's a little box here, which is a USB data logger. So that talks to the ultrasound, and it's also talking to this black plate at the bottom. That will record pressure on the plate. In fact, it records force. And you can do that up to 1,000 times a second. I think the ultrasound can go up to about 200 times a second, something like that. So you control that with a little laptop. You can see mine in the corner there. And what you do is you press go, and it bounces ultrasound off the ball, and you record what happens next. So this ball will fall under gravity, and it bounces on this plate. And usually, if you drop it, with a bit of dexterity, you can get it to do about 5 or 6 bounces before it bounces out the beam. Which is why you don't want to have if you're a teacher on this call and you want to do this at school, don't pump up your ball too much, because it will bounce once and then disappear, and you have to go and find it. So you actually want to take some of the air out of this. All right, so what sort of data did you get? There we go. Apologies for some very bad handwriting here. So I hope you can sort of see this, but it's about 569 grams, something like that. And you've got this, I'm sure you probably can't see the annotation here, but this is velocity versus time. Sorry, that's vertical force versus time is the top graph. There we go, force versus time. And what you see is a sort of sharp impulse with a little bit of ringing afterwards. In that time, the velocity time graph increases and then rapidly decreases to a negative. So velocity is measured sort of in the downward direction. So it accelerates under gravity. Although it's not quite straight, it's not bad. This kind of first part will be about 9.8 meters per second squared. And then you've got this sort of rapid change of velocity, almost linear. And then it will rise with a slightly smaller upward velocity. That's because we have very much an inelastic collision, particularly if your ball is particularly flaccid. So we've got from about 3 meters per second to about just over 1. And then we have another bounce a bit later. And then if you plot displacement versus time, you get some parabolae when it's in the air. Okay. So what would be quite nice is to, can we model this motion? And this kind of graph, almost certainly all of you, if you've not experienced an A-level classic mechanics problem, this is one that crops up time and time again, how you draw the graph. Of course, the trick is that you notice the time between the bounces gets a bit smaller. So let's go and explore this. Let's go back to my screen. So here we go. I think I've got a nice little animation to show you first. So I've got 2 bits of code. We're going to go for, this is all, you should be able to download all of these from my websites. And what we'll do for is ball bounce. I've got 2 of these. So I think one of them, ball bounce, that produces a little video. Hopefully this will work. Okay, there we go. Let's make that a little bit smaller. There we go. So it's worked out what's going to happen next. And then we're kind of bouncing a ball. This is probably not realistic in time. There we go. I set it to be going to 4 seconds. So it bounces high, and every time it bounces, it loses some kinetic energy. And there we go. So the little black star is where we start it from. So I'm assuming this ball is dropped from 1 meter. Okay. So let's go and plot this. So this one's got some stuff involving videos, so that will be a bit irrelevant. So what we're going to do, this is the code we've got. Now, some of you might be wishing to do some live coding here. What you might fancy doing maybe is take a screenshot if you've got 2 of you working on this. Otherwise, just sort of get some ideas of how I've done it. And of course, these videos will be available. So, so what we've got, this is what's inside MATLAB, which is probably my favorite kind of language to prototype some ideas. I say prototype because if you were making a kind of a simulation which you're going to use a lot, this is probably not the language you would use. You do C++ or C or JavaScript if you want to do it via a website. But I find sometimes there's a lot of stuff going on that's not related to the physics you want to use. So in terms of figuring out how your simulation is going to work, MATLAB or Python gets you there much quicker. So a lot of engineers will use these to start things off. And it was quite nice is that the interface, the IDE, the development environment is really intuitive. So what we've got is a text window here, and green stuff means commentary. And in MATLAB, that's preceded by a sort of percentage sign. And then I've got a function, which means things happen within this and are not exposed to the outside world, which is my command window. This is like a calculator. So if I do, for example, x equals, I know, sine of pi on 2, all right, I can use it like a calculator, all right, but I could do much more than this. And what I'm doing is I'm defining various things. So you can see I've got my inputs, and a really good thing to think about in this course is that is the idea of computational thinking. So what do I mean by that? I mean, when you're doing a physics problem, you're thinking, right, what are the inputs to my model? What are my kind of processing kind of things? And what are my outputs? So in this case, I've got a ball, right? It might have a mass. It's got the drop height. I don't know quite why I've done 28.1 meters here. It's 0.281, but there we go. Maybe that's exactly what we did measured in class. 9.81 strength of gravity, and that should have some units. All right, we've got the coefficient of restitution, which is, tell you what, if you can define that, put that in the chat. What is the coefficient of restitution? What have we got, Nina?
Yeah, we're starting to get answers. A ratio of speeds before and after a collision. Separation energy over approach energy. Speed of separation over speed of approach.
Marvelous. So the last one is probably the best definition. The second one regarding energy, it's related, but not exactly that way. So if you're looking at collisions, if it's not an elastic collision, that means some of the kinetic energy is lost. So you'd have thought what you want to do is a kind of ratio of kinetic energy after the collision to the kinetic energy before. And that will be a very sensible thing to define. But it turns out mathematically, it's a lot easier to think about the ratio of the speeds. So C is defined as the speed of separation divided by the speed of approach. Okay, and that's a kind of linear thing where if you think about it, kinetic energy goes as speed squared. So mathematically, we've made it a bit, well, twice as complicated. All right, so this is a nice thing to define. So c equals 0 means splat. It's like you drop some jam, right? It doesn't bounce at all. It's a totally inelastic collision. C equals 1 is completely elastic, so things will rebound with the same kinetic energy. And so C between 0 and 1 kind of is more what reality is. We can, of course, get more than 1, which means we've got some explosives going on. There's some sort of energy released every time it drops. Okay, so what we're going to assume here is we're going to assume a bounce time. So for my force versus time graph, obviously it's going to be quite complicated what happens exactly in there, but we can model a bounce as a sort of triangular force versus time, a kind of impulse. And the width of that triangle, I'm going to say, is about 200ths of a second. We're going to stop the simulation after 20 bounces, and we're going to run things in a loop every thousandths of a second. So I can think about what happens between the bounces. Now, it turns out there's a very nice little formula for the total time to stop bouncing, and we'll come to that in a minute, and indeed the total distance travelled. But we'll come to those a little bit later. So what you have to do first is we're going to initialize some arrays of displacement x, velocity v, time t, and also force versus bounce times for between our bounces. So what we're going to do is basically apply constant acceleration motion within a loop. And it's amazing the number of things you can do with this simple idea. So if you can, x is ut plus a half at squared. See if we can see that here. There you go. Except what I'm doing is I'm saying I've got constant acceleration motion between my time steps. All right, so that's a really nice idea, because what we can do is we can change what acceleration can be. You could have anything like, rocketry, electric fields, magnetic fields, but between our small time steps of a thousandth of a second, we're going to say the acceleration is constant and evaluated by whatever formula we want. In this case, it's a constant acceleration at g going downwards. So what we're doing is we're nibbling away at our displacements. We're taking away half g delta t squared, and we're taking away v delta t. Remember, v is positive going downwards. And then we're adding g delta t to our velocity. So essentially, this, we could use this for projectiles, whatever you like. And then we're incrementing our time. Now, the difference between this and a projectile simulator, of course, we have a bounce. So what are we going to do that? Well, when you think about it, if we work out what happens next, and remember, we're nibbling away at our displacement. It starts off at h, which in our case is 0.281 meters. If the next displacement is negative, obviously that has no reality, but because you can't move through the force plane. But if it were, that's basically right. We've reached the surface. Okay, so that's a bounce. Now we've got to have another one, and that's the velocities heading downwards. Because if we didn't have the second criteria, once the bounce has occurred, we're still kind of below the surface, so we'll be forever kept at the force plate, which obviously is not what happens. So we've got a logical condition here, and I'm using an if statement, all right, which is very similar to many languages. So if the next value of my displacement, xn plus 1, is negative, and my velocity, the next velocity is positive, then I've got a bounce. So what do? Well, I'm going to add 1 to my bounce counter. So a counter is a nice thing. This is just an integer. And this little bit of code here tells me what the time is and what the force is for my bounce. So I've got the, so TB, I think what we'll do, actually, I'll evolve this. I'll put a breakpoint here and I'll run this code and we'll see what happens. So here we go. So we've had the first loop and we've got, so how many? So n is now 240. So actually we've been around this whole loop 240 times already. And my velocity has now got 241 values to it, my displacement and my time. Okay, and if we can look at that in a spreadsheet, if you like. So MATLAB gives you something that looks like a spreadsheet. Here you go. So these are all my times, and you can inspect those. So every time we go around a loop, I essentially add an extra column to my spreadsheet. Now, so TB, we've got 3 values. Why is it 3? Well, I've got the time of the bounce, 0.24 seconds, and I'm adding either side a little bit of my, so what have I done? I've got, yes, T bounce, so half a bounce time either side of that. So what's that going to be? 0.01 of a second. So the idea is that my force versus time is going to be a triangle. So I've got the time where it starts, the time of the bounce, and the time when my sort of force versus time has ended. And you can model that by, I've got 0, I've got this thing here, which is basically the rate of change of momentum. So the mass times the velocity, I've got the coefficient of restitution plus 1. So c equals 1, that'd be 2. And then I've got a factor of 2 here as well. Okay, so that's my max bounce force. Just thinking, is that there right? Should I actually have a 2 there? I'm going to keep that as there for the moment. So there we are. And then what I'm going to do, now I've had a bounce, I want the main bit really is this line here. So what I'm doing is I'm swapping the sign of my velocity and I'm scaling it by the coefficient of restitution. All right, so that means my velocity vector is now going the other way around. So Vn plus 1 is, let's just type that. So Vn plus 1 is 2.35 meters per second. And if I increment this one more time, if I take a step, all right, it's now minus 1.67. Okay, now I increment my counter and basically I keep going around this loop. All right, so let's just quit that because there's lots of loops. So if I take a breakpoint here, all right, that happened very, very quickly. N is now 1,403. Look how fast that was. I mean, this is the power of computing, everybody, is that, you know, we can do a repeatable object which would be boring to us in a fraction of a second. And then all the rest of it is just literally plotting some things. So I think what I'll do is just sort of step this, see if it works. So step this one. So we've got a graph. And what I'm going to do is I'll show you how that evolves. Yeah, so what I'm doing, I'm making these subplots. So here's my displacement versus time graph, and I'm going to add some more, and you'll get what you have here. If we just run the thing, you can see what it looks like. Here we are. So bouncy, bouncy ball. If I move that into the window. Here we go. Let's make sure that's visible. There we go. So what we've got is you've got displacement versus time. Those are my bounces, and you'll notice the bounce time, or the inter-bounce time, gets less and less. Let me just stop that stopwatch. There we go, between the bounces. And this is the sort of graph that probably your physics teachers will set you, is what does the velocity time graph look like? This sort of sawtooth. So you can say it's accelerating, g, and then we have our bounce, but it's not the same velocity because we've got a coefficient of restitution, which in this case is 0.71. So that's our ratio there, and it goes, and then it keeps going back. All right. We also got the force versus time, and the area under that little triangle should be the change in velocity times the mass of the ball. I just noticed there's a rogue factor of 2 there, so I might want to check that. But anyway, that's the idea. The area under this graph, the force time graph, is the impulse, which is going to be the change of momentum of this one. So this should all hang together. Okay, so that's my bouncy ball. Let's just go back to the presentation and I'll field any questions that might have arisen. So any questions have come out of that?
Yeah, we're dealing with them.
Brilliant. So I can't recommend enough. If there's one simulation you want to do, is apply constant acceleration motion in a loop and just have a mess around with what the acceleration versus time looks like. Start off with projectiles, and then you can move to windage, rockets, all sorts of things. Okay, so that's how we can make motion happen. And notice, you know, we've not had to do any nasty calculus here. We've literally done it in a loop, because essentially we are doing calculus if we take our time steps to be small enough. Right, so a little bit of maths. I'm just going to kind of point out a few things, but this is actually a bit of analysis you might want to do. So here's my ball, it bounces. So root 2gh is the speed it hits the floor. And so c root 2gh is going to be the velocity that I'm bouncing upwards. And so if you think about it, if we use conservation of energy here, so half mv squared is mgh. So my height's going to go with the square of the speed. So given my speed is proportional to c, my height's going to be proportional to c squared. So basically, the heights I go to go as powers of c squared. So the next bounce goes c to the 4h, the next bounce c to the 6h, etc. Whereas the velocities will go in even in the sort of linear powers of c. So here's my distance travelled, and what you'll notice is we've got a geometric progression here. So you've got to sort of like, it's not quite exactly a geometry. You've got to sort of, play around with it to get 1 plus c squared plus c squared squared, etc. You've got to divide by 2h and then add a half. But if you can cope with that complexity, you've got a description for your distance travelled as a function of the number of bounces. And because it's an infinite series, you can work out how far exactly it will travel, including it based on h, your initial drop distance, and your coefficient of restitution, which is rather nice. And in fact, however, the time is probably a bit more interesting. And it's the same kind of idea, but you're working out the time of flight for each bit, all right, because it's projectile motion there. So the height is a half a t squared. So 2h over g square rooted is going to be the time it takes to go one of these routes. And because the distance travelled goes as c squared, that's why we've got this sort of, and that's in the root, which is why we've got this multiplication factor in front. So it's another geometric progression. And what you end up with is the time of bouncing, how that relates to your coefficient of restitution. And what's quite a nice thing to do is to rearrange this. So actually work out c from the bounce time, h and g. Now you can say, well, hang on a minute, and that's actually a finite time. So you can record that. If you drop a ball and you time how long it takes before it stops bouncing, you can use this formula to work out c. So that's a lot nicer. You can time 20 bounces, with quite high precision, whereas to time one bounce with a stopwatch and a ruler would be subject to a lot of errors. So there we go. That's something you can have a little play around with. Maybe a nice Excel sheet, perhaps. So there we go. That's the bouncy balls. This is another classic experiment, especially if you're taught by me. And if you've never done this, get yourself a basketball. You want to pump this one up, definitely. Get yourself a nice fresh tennis ball and drop them. And children will smile if you do this. Although if you break any lights in your room, maybe they won't. But just watch out for that. So this is the formula for it. It looks quite exciting, and it's a subtle application of conservation of momentum. But you've got to consider the ground big ball bounce and then the big ball little ball bounce. So if you go through this, you end up with this sort of rather nice formula for the ratio of the heights. It involves the coefficients of restitution. So C1's the ground ball and C2's the little ball, big ball. So in the limit where they're both elastic, you get this rather nice expression here. And if you take a limit where the mass of the big ball is much bigger than the little ball, then that disappears. You end up with 3 over 1 squared, or 9. So our little ball can rise to 9 times the maximum height. Going through that with Alain will be a nice interview question for university, I would suggest. Okay, so what you could do is maybe put that into an Excel sheet. Here's an Excel sheet. This is one I did earlier. Hopefully it's over here. So for those of you who might be totally new to programming, you think, oh gosh, I'm not quite ready to use Python or MATLAB to do something in a loop yet, but I'm okay with Excel. This is a great way to start. In fact, I would recommend, as soon as you see a formula, something that's new, make yourself a calculator. So this is a visual calculator with the maths in it. These are my inputs. All right, these are big M and little m. I've got my coefficients of restitution. Remember, you could figure that out from dropping it and timing the bounces. Here's my drop heights, and then I've got these sort of heights here. So I've got, so that's a sort of my ratio to the speeds, these ones. And this is my predictions. I'm evaluating this formula here. It looks a bit complicated. It's got sort of cell references. But what I've essentially done in Excel speak is evaluated this. So I think it's a really good idea to put pictures into your Excel sheets. Don't just have numbers and things. So it's a kind of live calculator. So I don't know, let's say we've got a coefficient of restitution of 0.7, right? That's the ball on the ground. We predict it will go 2.7 meters here. And if this one was, say, a little bit more flaccid, 0.8. Actually, let's go a bit more. Let's go for 0.9 for this one. There we go. And if we go for a bit closer to 1, all right, that's 1. There we go. So that should be, oh, that's interesting. Why have I not got, no, yes, because these mass ratios are not 0. So if I make that really small, like 5, you'll notice that's getting closer and closer to 9. There you go. right? So there we are. Our tennis ball mass is, very small fraction. So there we go. So numerically, you can explore the limits of your formula. Okay, any questions from that?
I guess quickly, why not? How is the geometric progression worked out? Is it just by looking at the data points?
Oh, right. Okay. So if we just go back again, this is you probably want to eyeball the theory and work it through with a pen and paper. I think probably the time one's maybe the easiest one to do. So again, you can get this off the eclecticon if you want to have a look at, but these are the sort of stages. So the key thing is to notice that if root 2gh is the speed it hits the floor, then c times that is the speed it rises. And every time we do that, we're going to multiply it by another c. Okay, so that c squared root 2gh is the next bounce. How high does it go? Well, if you use v squared, is 2gh from kinematics, then you'll notice it will rise c squared times the previous height. So every time we need to multiply the maximum height by c squared. So if you want to work out the time traveled after n bounces, then what we've got is essentially, so distance is a half gt squared, right? So what you're doing, if you put in your c to the n h, or c to the 2nh in here, you'll end up going to get a nice c on the outside, or c squared for this one, etc. So basically, you work out the there and back time for each bounce, and then if you sort of multiply by root g on 2h, and then divide by 2, and then add a half, you turn the time here into a geometric progression. And that's the formula for a geometric progression. If you use a nice proof, we won't do that right now, but that's a really nice little proof to do in maths. If you haven't come across that, I do ask your maths teacher or look it up in a book, or you can go on my website. But that's the answer for that geometric progression. It has a closed form answer that I'm circling at the moment. All right, and when you make n go to infinity, because c is less than 1, that just disappears on top. All right, so inverting this formula, so making c as a function of t, h, and g, is a nice way of calculating the coefficient restitution given measurements of the other things. All right. Okay, so what else we got? Okay, so talking about some balls. Yeah, I mean this is how you work it out, but I'll let you have a look at that in slow time. So we don't have to be sort of limited to bouncing in one dimension. So there's something called the zero momentum frame. And basically what you do is you take some balls which are colliding and you imagine a kind of velocity. In fact, it's the mass weighted average of the velocities. If you run at that speed, what you'll see is a zero momentum. In fact, you calculate it by summing the momentum minus our new velocity of the two things and set that to be 0. That's what defines V. And so that means is that, I don't know if I've got a nice picture here. Here we go. So here's my sort of before impact. If you're in the zero momentum frame, so you run at this speed, you must have zero momentum. So in other words, the arrows have got to be facing each other. So u2 minus v and u1 minus v look like this. So what's going to happen? They're just going to collide. And the new speeds will be that multiplied by the coefficient of restitution. So what you do, if you want to find out what happens next, you need to sort of subtract v from the velocities, collide, and then add v back. And so you end up with a really simple expression for what happens next. It's literally, if we know what our zero momentum frame velocity is, and we know what c is, we can work out the result of our collision. It's literally this formula here. Okay, so that's something you can apply in 2 or 3, even 3 dimensions. And I'll show you a little demonstration. So here we go. I've got, this is under balls and box. There we go. So if I run this, and there we are. I've kept to sort of 2 balls. Let's make that a bit bigger. This runs for 10 seconds. There we are. I'm going to run. I hope it doesn't want to crash. There you go. So I've got it loses a bit of energy. The coefficients of restitution between each other and the ball are not 1. And it also will accelerate. It will sort of fall as g between. Well, obviously, you see it's hit the floor now, so it's not going to do that. But it kind of has a sort of realism to it. Let's wait till it gets to 10 seconds. And then here we go. So there we are. They're bouncing off. There we go. There we are. That's quite nice, isn't it? So to code that up, there you think, oh, that's complicated. That looks every motion, is really difficult. Well, actually, the code is really simple, and I'll just show you what's inside that. So if we go to, let's get rid of that one, balls in a box. All right. So what we do is these are my inputs. Those are my radii. So I've got a sort of 2:3 ratio for ball masses. These are my coefficients of restitution, my initial speeds. And there's a bit of plotting stuff going on, but what's the action is this while loop here. So I've got some this is the sort of initializations. I have to work out whether my balls are actually overlapping. In other words, I have a collision. There we go. So this is the actual sort of main loop. I increment time. I've got my constant acceleration motion, just like we saw before, but for both balls. And then I've got this sort of check if a collision occurs. In other words, I look at the distances between the centers of the balls, and if they are less than the sum of the radii, I deem a bounce to have happened. So that's what this function does. It looks at the wall or the balls. And if you just have a little look at what we've got, here we go. You'll see we've got the zero momentum frame, and we've got the zero momentum frame minus the coefficient of restitution times the difference between the velocity minus the zero momentum frame velocity. And so that's the only bit of code which we need to work out the bounce. Quite good, isn't it? The only thing we need to add is this little thing here, which this says whether the separation between the balls is less than the sum of the radii. Because obviously a bounce can't have happened otherwise. So that's basically it. I was a bit more sophisticated than what you just saw, but the whole thing is only about 150 lines, and I spread it out. So you could code this up in an afternoon. Right, so let's go and have a little look. What else we got? Right, so if we move to forces, to check the time, this is or kind of moving in sophistication, really, in terms of sort of apps. So, if you've not got a kind of collision, Newton's second law really is what defines motion. And so here's an app that I've made where you've got a tame cat. This is Sybil the cat who's sliding down this slope. And she has a little tow rope applying 35 newtons of tension. And in fact, actually, she's going up the slope. Her acceleration is 5.75 meters per second up this slope. And what you can see is we can see the vector sum of all those forces. So we've got a normal contact force, the red one. We've got the tow rope force, adding tip to tail. We've got the friction force here. And we've got the weight of the puss, which is the purple one. And those don't form a closed polygon. So we have a mass times accelerator, resultant force. Right, let's go and load this little tool. So I've got this in a separate place. If you've been downloading my code, I've got there we go, apps, and I've got some other things as well. So code and apps. The apps are slightly different. So sort of thing for the computational challenge, many times lots of people have made phone apps which are amazing. So if you are really keen and want to shoot for a gold, that's a good thing to do. So let's go and have a look. Lots of these little programs. We want slope. There we go. So if I run this, hopefully the cat should appear. There you go. And so if I just make that a bit smaller. So what you got is here's your cat on the slope. And if I fix the axis scale, I can modify the angle of the slope like this. There we go. And everything dynamically changes. And that's what's really nice about making an app. You're creating an interface for humans, and you want to control, these parameters, and that's it. Nothing else is displayed. You get just what you want. It's a really kind of creative thing to do. So we can change the cat mass, and you can see everything changes, strength of gravity, the rope angles, and you can sort of see how all these graphs move dynamically. Good for setting problems if you're a teacher, and good for exploring the situation if you're a student. All right, so for example, so we've got, if I remove my sort of, if I can make my rope tension get a bit bigger, so we go from downhill, and eventually what you'll see is the acceleration gets smaller and smaller and smaller downhill until we get to some form of equilibrium. So there we are, nearly there. And you can now see acceleration getting to zero. And now we've got static friction acting uphill. Okay, and then we can keep going until eventually our friction acts the other way, but we're still uphill. And then eventually we start to accelerate uphill. Okay, so you can start to explore all the situations. All right, so there we are. What else we got? A few more little examples. So this is a water rocket. I do have a nice little video of this, but basically what's going on, Newton's second law, a bit more complicated than projectiles. We've got thrust, and thrust is the mass per second, which is mu, times the relative speed of fuel ejection. So I don't know, what have I put here? So mu, actually, yeah, it's about, I'm going to do some maths on this one, but I don't know, a few kilograms a second, something like this. And then once, of course, all the water's gone, there is no thrust. You've got the weight and you might have drag. So that might be, it's a drag, a good model of drag for aerodynamics. It goes as the square of the speed. And by using V times the modulus of V, that means our drag always opposes motion. Of course, that would make it a nightmare to actually integrate calculus-wise, but we're not even going to try. We're going to do it in a loop. So here's one I did earlier, and it's, there we go. I think I've got a slightly better picture than this one, actually. Let's look at the rocket. Here we are. So again, there's a lot of plotting things going on here. But my rocket model itself is this one. So you can just maybe see a few things. We've got our mass ejection rates. We've got our dry mass of the rocket. And we've got a trajectory in a while loop. So I've got this little flag saying, has it hit the ground yet? And I calculate all the parameters. And eventually, here we go, thrust, weight, and drag. And that's my calculation here. All right, so although it's in programming terms, it's not too different to what you do from writing down maths. So let's go and run this and see what happens. Let's just change the folder. And it should take a little wee time. So I think I'm running this in a loop for varying the parameters. And hopefully, here we go. And I should have a picture. Here we go, rocket model. And here we go. So I think it's this little unrealistic set of parameters I've got here. My wee water rocket doesn't really go 67 meters. Probably more like about 30 meters, but it's still quite impressive. You get them for about £10 from the Science Museum. It's a brilliant little piece of kit. All you need is a lemonade bottle and a bicycle pump. So, but you've got some nice curves. Here's my apogee. It looks kind of like a projectile, but of course we've got our thrust phase. And a nice thing to do is to overlay the forces. So thrust, weight, and drag are all computed separately. So initially have a really huge thrust, which then diminishes as we remove the water. Our drag increases as we get to the maximum speed and then decreases. And then we've got our weight, which obviously is tailing off to the weight of the dry rocket itself. So by plotting all the three curves on top of each other, you can debug your code. And in my case, we've got a really ridiculously large initial acceleration. So is that actually correct? And we probably need to go back and look at some of the particulars of our inputs. But so this gives you some diagnostics. So getting graphs that actually give you the numbers you're interested in, like the time of flight. So you could time that with a stopwatch, see if you're nearly correct. And if you're really smart, you might be able to actually work out with maybe a theodolite or something like this, exactly how high your rocket goes. I've not managed that yet, but maybe some of you could. All right, we're getting close to the end now, so I want to go and show you a few other little bits and bobs. Right, so we've looked at quite a lot of mechanics. Let me just make sure that's wrong one. My mouse is not looking too well. There we go. Right, so I think this might be the last one, actually. Yeah. So of course, we've looked at linear motion pretty much so far, even the rockets, going through up and down. So quite a nice thing to do is look at circular motion. So it's quite a busy slide this. So what's going on? Well, what we've got is a kind of track, which is an arc of a circle of height h. And we're going to roll a cylinder or it could be a sphere along this thing around a loop the loop. And in a certain situation, in fact, this one, so rho defines whether it's rolling or sliding, and sigma defines whether it's a cylinder or a sphere. All right, so if we've got a rolling cylinder, for example, rho is 1. and that's a half. So 7.5 divided by 4 times the radius of my my sort of track here minus the radius of my cylinder. If my height is bigger than that, basically what it will do, actually I think that should be an equal sign actually. So what it will do is it will go all the way around and then fall off and go to here. And you can see that like a trail I've plotted. So you think, oh, I can't really understand this. Let's do it. So let's look at it. Let's look at it dynamically. So I'm using pretty much the same idea as a loop, constant acceleration motion, but of course my forces are going to be different here because I'm constrained to a circle. So if I go and run this one, loop the loop, no, it's roll the loop. There we go. Let's just make sure I've got that in the right place. It is rotational dynamics. Roll the loop. Here we go. There we are. So I can make movies with this, but I think this should be smooth enough to see. Right, so here you go. So I'll just make that a bit bigger. There you go. So we've rolled from here. We've started from rest. I think it repeats. There we are. And I'm sort of like got a little spot on the side of my cylinder, which tracks its motion. You get a nice cycloid. Then it falls off. And the criteria I gave you, it's not easy to work out, but it is possible. It's in my Science by Simulation 2 book. You could work out the ratio of the heights so that it falls off the circle and hits directly at 0, 0. We can go a bit faster than this, and then it will go all the way around. So let's do that now, actually. So if I go to, do I have the ratio here? Here we go. To make it all the way around, this is the criteria. So rather than a 7 here, that's got to be a 5, and that's got to be a half rather than a quarter. So if I run this, that should hopefully allow you to go all the way around. So you notice it's gone a bit faster. Oh, it's getting there, it's getting there. And there we are. It's now made it all the way around the loop. Whereas the other one probably be a bit dangerous if you made your carriage fell off the loop and crashed at the bottom. I'm not sure you've been in business very long, but this one could be a bit safer. So there we go. So lots of possibility with motion, almost an infinite possibility. All good physicists should start with mechanics. And I think everybody, sort of rite of passage is to make yourself something dynamic. It could be a solar system simulator. In fact, that was the BFO challenge. I think it was the second year. So that would be, well, yeah, the second year we ran it. Yeah, pick something that you can do. A little projectile motion simulator would be nice. A bouncy ball, something that's interesting, and go make one and make it animate. So, do we have any final questions? Other than that, we'll call it a close today, and then we'll meet again next week. Any more questions?
Yeah, there are a bunch of questions we are replying. Will the astrophysics lesson be next week?
Oh, that's a very good question. Possibly. I'm sure that can be possible. Yes.
Okay.
And if it is, I've had a little project. So if you came last year and thinking, oh, it's just going to be the same as what Dr. French does every year, not quite. I do kind of improvise a bit. However, I have been engaging in my own little personal project on some astrophysics for Science by Simulation 3 and for the amusement and enjoyment of my students. So there'll be some new things for the Astro course. So I've downloaded 50,000, a star catalogue of 50,000 stars, and we're going to make a Hertzsprung-Russell diagram. And so I'll see if I can make sure that's on the website so you can download it too. All right. Okay. Any more questions? Let's come out of that.
Yeah, we're going through them all good.
All good. Right. Well, in that case, I'll come back to the splash screen and we'll take a pause. Thank you very much indeed, everybody, for coming on a, well, I'm sure you're indoors on a rainy Thursday evening. How do I stop sharing? There we go. Marvelous. And yeah, enjoy, take on a project, try something of those. If it's just an Excel sheet to model a kind of a formula or the double ball bounce or whatever you want to pick, or could always be an animating app. Wherever your skills are, see if you can push them a bit and make yourself something that works. And I think that will really propel you into the future. But I think, yeah, if there's one thing you want to take from this, and that is that a loop of constant acceleration motion, that is extremely useful. And given it's one of the first things you'll learn at A-level physics, to actually be able to apply that for really complicated forces is a really powerful idea. So give it a go. All right, so see you next week.
Just wanted to say quickly that the link I have sent another email with the right link to last week recordings. The link in the recordings in the email was an error. So it wouldn't have worked.
It's a computational challenge of all, this. Right, you're gonna have to go home now. I've got a date with a cup of tea. See you next week.